Good morning or good afternoon, depending on where you are. Welcome everyone. So today we're very happy to have Dmytro Volin, and so he will tell us about the Bethe ansatz and what it is more than an ansatz.
Okay, thank you. I presume I can start. By the way, I have a question. When I do like, okay, still it's not good. Okay, I'm starting now. So thank you for inviting me to speak on the literature club. So today we'll speak about completeness of Bethe equations. So this is a project which was recently finalized with Sebastian Laurent and Dmitry Chernyak. You probably all know Sebastian. Dmitry Chernyak is actually currently a master student at École Normale, and he will start PhD next year with Jasper Jakobsen and Hubert Saleur. So he was my intern. He did an internship with me at Trinity College Dublin, and like half of the work was done back when I was in Dublin. So the second part was done when after I moved to Nardita and Uppsala. Okay, so talk will be quite mathematical, and I do not know how long he will survive. So I decided to start with actually stating what is actually I'm going to tell you. Okay, so there are four statements actually that are going to be discussed today. The first statement is the one which you all wait, is completeness itself, is that algebraic number of solutions of good Bethe equations is always the right one. Okay, so the second
functional number.
Sorry?
No, sorry, it was a joke.
I didn't hear it anyway. Okay, the second is faithfulness. And faithfulness that there is a one-to-one correspondence between distinct solutions and eigenstate of the Bethe algebra. The third one, it's like a bonus which coming from the first two. If the Bethe algebra is diagonalisable, then the joint spectrum of its commuting charging is actually simple. There are no coinciding solutions. It's like a theorem. And this fourth one is very practical. We found a new way to explicitly parameterize solutions to Bethe equation using standard Young tableau. And it will be the very last part of my talk, and there I will connect to string hypothesis. So disclaimer, we do not use string hypothesis in the proof. The proof is rigorous. No assumption is being made of any kind.
Sorry, one quick question. What do you mean by good Bethe equations?
Well, this I will explain, of course.
Okay.
Right, so just tell you what you want. This picture is actually about explicit parameterization. This is a standard Young tableau. And from this standard Young tableau, I have a mathematical program to generate reasonably efficiently solutions to Bethe equations. I will explain at the end of it. So now let me explain in more detail this restatement on the example of, well, SU2 Heisenberg spin chain. Okay, this is the one which is spin up, spin down, and this is famous Bethe equations written for homogeneous case by Hans Bethe. But we will study arbitrary thetas. There will be no, well, we will see. So basically, essentially, there is no restriction on thetas. As answers, the statements will be for all of them. But they're also needed for the proofs. You can put them to 0 if you want, but they're needed for technology of the proofs. So first thing to recall that if you want to count solution to this equation, you have problems. First of all, coinciding beta rules should be discarded, but sometimes it's not the case. If you fine-tune twist to some particular values, then if there is difference, I mean, if difference is equal to h bar over 2 or h bar, then you have 0 over 0 situation, infinity to infinity situation. You have to regularize, and sometimes this exceptional solution are physical, sometimes are not. So there are some troubles. And actually, finally, solution is not to deal with troubles and just choose different equations. So good equations, Andrea, there will be different versions of them, but the simplest one I can write is Wronskian Bethe equations. So what we do, we take beta roots, assemble it to do Baxter polynomial. So for m magnons polynomial of degree m, and then we say, okay, this Baxter polynomial, it's Wronskian with some other polynomial q tilde. should be equal to this function, proportional. So everybody is monic, like Lin coefficient is equal to 1, and so normalization coefficient is such that everything works. So this is like after Pronkov-Stroganov is kind of Baxter polynomial beyond equator, but it's historically. So this polynomial of this degree, just to make Wronskian of degree L. And what we actually are doing, we say, okay, we want to find all solutions to this equation when Q and Q tilde are polynomials. So in reality, what we are doing, we say, okay, Q is a polynomial, it's parameterized by its coefficients, and Q tilde is a polynomial parameterized by its coefficient as well. Of course, if we add Q to Q tilde, value of determinant doesn't change. It's symmetry of the system. So we actually, coefficient in front of UM can be set to any value we want, just is not physical, we can just kill it. So all coefficients except for this one are actually physical, and there are exactly L of them. And eventually, when we equate left-hand side polynomial to right-hand side polynomial, each coefficient to each coefficient, we get this equation, where chi is actually elementary symmetric polynomials of theta. So this is what we call Wronskian Bethe equations, and it's for them we actually state in the completeness property. And then the statement that, okay, if you solve this equation, then take your Baxter polynomial, and well, then this UI will solve normal Bethe equations, but we only track of physical solutions. We do not track of any exceptional situations. I mean, all exceptional situations that are physical are automatically included, and that are not physical are not there. So this is a statement for GL2 case. Right, by the way, just a reminder, this is the number of solutions that we are going to get for GL2 case.
I cannot see the last line somehow.
This line you do not see?
Ah, no, I can see it now, sorry.
You have to zoom out, right? Okay, so now it's about completeness. What about faithfulness and simplicity? Well, the point about faithfulness is that, well, this is just some polynomial equations, but you know that Q's are also, these are Baxter Q operators. And faithfulness basically tells you that all solutions to these equations are in bijection to eigenvalues of Q operators. What is needed to be proved exactly will be discussed later, but this is the basic idea. So there are no unphysical solutions, so the one-to-one corresponds, okay? And so simplicity already explained, but let me notice now that Bethe algebra diagonalisable, for instance, if it's invariant of the Hermitian conjugation. So if all thetas are real, that is the case. And so for all thetas real, we know for sure that all solutions are distinct. And it's a very powerful property from the point of view of physics. Okay, so this is type of questions we are going to discuss. And now, so for which models the statements actually applied? So we consider GLM/N a rational spin chain in the defining representation. Defining is vector representation, like M plus N dimensional.
Sorry, when you say non-degenerate, so if you don't have twists and there are multiplets, it's the highest weight only.
Right, except for multiplets, right? For highest weight, yes, that's right. Statements apply for these spin chains, both for periodic boundary conditions, and there is no twist, and for non-degenerate twist case as well. So in this talk, I will cover only periodic spin chains. This is actually more technically difficult task than twisted case, but it's actually much more fun and much more interesting things to discuss. That's why I decided to do periodic case. So historically, rigorous proof of this statement was done by Muhin, Tarasov, Varchenko for bosonic case. And okay, so now we generalize it to supersymmetric case, but there are also some non-trivial tweaks we introduce. Okay, we'll discuss them. So it's not like bolt put super everywhere. It's more than that. So I also have put the names of the articles, because the main article is this 2013 one. It's really the main one. And this is called Spaces of Quasi-Exponential and Representation of the Yangian. It was not even quantum algebra, it was algebraic geometric archive. And so no surprise, not many people know about it. Well, I have to say to Dmitry Cherniak, who actually found it and was able to understand it. So it's, well, it's not easy paper to understand. right? So Gillian case was proven here, and we do supersymmetry.
Can I just jump ahead and ask whether these sorts of proofs are going to generalize to spin chains with higher order interactions? You know, next to leading order corrections, or obviously, you know where I'm heading, the ADS type spin chains.
No, for DSCFT situation is quite good because we have basically continuous. I mean, you can take coupling constant set to 0. So the only proof I can give you is that okay, coupling constant is continuous variable, so send to 0 count there and then deform. So this will be of proof.
That's not. I mean, so there wouldn't be like a direct proof.
No, I'm not aware of direct proof. Yeah, so.
Yeah. But I mean, would these methods that you're going to tell us about, do you think they would be able to generalize, or they are very specific to one loop?
Many people are generic. The question, I mean, these methods really rely on polynomiality of your system, okay? So if your system is not a polynomial, you have to think much more. So as long as polynomiality it will generalize. If it's not, then it's, I mean, it's quite an addition that you have to make to the problem.
So something like the Inozemtsev spin chain?
Well, I do not know. So I did not study these classes. Yeah.
Okay.
Well, you will see after the talk and think for yourself if you can. But the one thing I can tell you is that if you want arbitrary unitary integer weight representation of this guy, which is kind of one loop DSCFT, right? So basically we know the answer, but I do not promise you paper soon because, well, answer is easy to write. It's difficult to explain all the details, but in principle, I know how to do it. Okay, so since we are mostly theoretical physicists here listening, and I need to do polynomial rings in my talk, I will do introductions. This textbook material from undergraduate course in Bachelor in Mathematics, basically. Okay, so it's part -1. So eventually, we want to solve these equations, and so there's some polynomial of c's equal to some value. And we actually do not want to solve them, we want to count number of solutions. So generically, the equation is the following. We have some number of variables, we have some polynomial, so we want to find the solutions. So how to do it, like how to formalize the equation? So we have to introduce this quotient ring. So what is numerator? Numerator is just ring of polynomial and variables. And for us, it will be important to think about it as also as not only as an algebra, but also as a vector space. So it basically spanned by vectors. Each monomial like is a basis vector. In the denominator, well, this symbol means ideal in the polynomial ring generated by PA, these polynomials. And by definition, the ideal is collection of all possible polynomials that can be represented as the following sum, where Q is also a polynomial. Okay, so this is all polynomials. I mean, they will vanish on our equations. Okay, and we take a quotient, like, okay, this algebraic quotient, but also it's vector space quotient. Basically, you can think about this, this equal to 0 is like linear dependence between different monomials. And we kind of take quotient, we using this relation, we exclude unnecessary linear dependence. And what happens at the end, that dimension of this vector space can be actually finite. Dimension of this vector space, of course, infinite, but this can be in principle finite. And there is a theorem that if dimension of quotient ring of the quotient ring is finite, then number of solutions to this equation is finite, and moreover, number of solutions coincide with dimension. So I will give you an example. So let's consider just polynomial ring non-variable and quadratic equation. So from here we see that all the powers 2 or bigger can be expressed as linear combination of x and 1, and that means it's 1 and x who form a basis in this space, and it's 2-dimensional vector space, and there are 2 solutions to quadratic equation. Since we are dealing with many variables, I will give you also one example of 2-variable system. It's more tricky now. So this is just tuned a little bit equation, but rather random choice was done. And so you have these two equations, and you want to ask, okay, how many solutions? So let's just do it in like school way. So first equation has either implies that x equal to 0 or xy equal to 1. If x equal to 0, this term is vanishes, and y is equal to plus minus 1. So if xy equal to 1, then, well, this term equal to 1, so y is equal to plus minus square root of 2. So we found 4 solutions to the system. You know the answer is 4. Now, can we count it in a formalized, like, systematic way? For this, actually, what we have to do, we have to compute, well, we have to find dimension of this quotient ring. This is our goal. But how to do this? For this, we first need to compute what is called Grobner basis in some monomial order. Like informally, what is Grobner basis? So these are some constraints, but like it's like primary constraints, and actually they can imply there are some secondary constraints and ternary and etc. So you have to find all possible constraints that follow from here. So this middle guy equal to 0 is a constraint which you obtain by like playing with these two together. You have to multiply this by y, this multiplied by x squared, subtract something like this. Oh no, maybe this is by x, I think. Okay. Anyway, so this is possible to derive this property. So this is immediate consequence of this one. And then lexicographic order y bigger than x means that every time I can replace y with x using some relation, I will do this. So in this case, I see that I have chance to replace xy with x squared. So here we have two x's, here x and y. So I want to replace all the time.
Sorry, could I clarify? So these three relations, what is I mean, the relation to the first two?
There's absolutely equivalent set of equations.
So they are also equal to 0, that's what you're saying.
They're all equal to 0, right?
Mm-hmm.
Yes, and I mean, set of solutions exactly identically the same. There's definitely not all difference. The difference that here all possible constraints are listed explicitly. It's important for counting dimension. I will tell in a moment why it's important. So basically, xy is replaced with x2 squared here, and you get these two equations. So these are three equations that we get. And now let's count dimension of w. So remind that we have this polynomial ring, and this is our basis vectors. Okay, we can all depict them as points in the first quadrant of the two-dimensional lattice. Well, I hope notation is clear. If not, please ask me. So, but now let's take a look. So this equation tells us in this Lex order that every time I see y squared, I want to replace it with this one. Okay, that means that all powers n bigger or equal to 2 will be not linearly independent. So this red rectangle means that I have to exclude them. Then this equation means that each time I see xy, I want to replace this with x squared, and that means that all these guys are not linearly independent. And finally, here we say that x power 3 or bigger have to be excluded this rectangle. So at the end, we have only 4 guys left. So 1, x, x squared, and y. And because, I mean, this mathematical statement that because it's a Grobner basis, it means we explicitly listed all possible constraints. We know for sure that these are linearly independent. There are no some hidden relation between them. From these guys, we do not know this yet. We need to do this one first. So they form a basis in W, in omega, and so dimension is 4, and we are done.
Just to clarify, Grobner basis is a function in Mathematica, right?
That's right. So about this, so every time you ask Mathematica to solve a system of equation, it's computed for Grobner basis. So actually, computation of Grobner basis is essentially, I mean, there are some remarks, but it's essentially equivalent to solving equations. Okay.
Just to add to this, it's in general very hard numerically to calculate a Grobner basis.
That's right. So that's right.
It's computationally this is tricky, but conceptually it's useful.
Yes. So computationally it's tricky, and so in the past, in 2016, we tried with Sebastian Laurent to find good ways to compute Grobner basis for Bethe equations, but we failed. Well, we reached length 15, but we did not find any nice pattern for generic lengths. And so in general, so Grobner basis always exists, can be computed at finite time, But in worst cases, and well, you never know when it's good and when it's bad, it's doubly exponential in number of parameters, computational time.
Yeah. Let me remind that Yunfeng and his collaborators also use the Grobner basis to solve Bethe equations.
Yes. So the question whether they found some efficient way to compute Grobner basis. So I mean, every time you solve a linear, every time you solve polynomial equations, any computer program will compute for Grobner basis. This is just basically theory of solving polynomial equations. The non-trivial question, which very interesting to ask, if there is any efficient way to compute Grobner basis for Bethe equations. And so if they found such an efficient way, this would be great. Yeah.
Dima?
Yes?
This figure in the middle, we used to call it a Newton rectangle, something like this, yes?
Well, it's not exactly
usually used for the description of algebraic curve.
Yeah, this is related to Newton polytopes, and there are some nice theorems about mixed volume of Newton polytopes and the number of solutions of Bethe equations, but we are not going to do it today.
Okay.
Oh, sorry, not solution to Bethe equations, solution to polynomial equations. We also tried to compute mixed volume of Newton polytop to count number of solutions, but we failed. Yes.
Dima, sorry, so just a simple question. So this Grobner basis is a set of generators that generate your ideal, right?
This is one of its properties. Second, its properties are all constraints are explicit there. There is no like constraints on secondary constraints, which is hidden. I mean, so these two guys generate your ideal, and these three guys generate ideal. They generate exactly the same ideal. But here, all constraints explicitly, you know that these are linearly dependent guys, but from here, you do not know it.
Okay.
Okay.
So as I remember, there could be a substantial difference in time depending on the ordering you chose.
That's right. But again, so this is an art to find a good order. Yeah.
Not a science.
Well, and also science, yeah. So there is no like nice theorem to say how to find, given just generic polynomial equations, there is no nice theorem to say, okay, this order will be good. I do not know such statements. Anyway, good news is that we are not going to use Grobner basis for computations. I only introduce Grobner basis here because this explicit example allows us to compute and make explicit checks. That's the only reason. We will compute the number of solutions differently. Again, so we tried to do Grobner basis, but we could not like make it work efficiently for large lengths. Okay. So since we also have inhomogeneities, and it's will be very important for our talk, let me also cover the case of parametric dependence. So we just take the same equations, but we add parameters now, right? Is chi1 equal to 0 is first equation, chi2 equal to 1 second equation. So in this case, I would like to work in the field of fractions. So curly, I mean, this round brackets means field of fractions since variables chi. So I treat them not as numbers, as some indeterminates. Okay, and this is just some field, and it's polynomial ring over some field, and we can again compute Grobner basis. In this case, it will be this one. So now it's again the same Lex order, and so now we see that y can be always expressed as a cubic polynomial of x. So all these guys will be not linearly, they will be linearly dependent, and then x4 can be expressed as a cubic polynomial. So these guys are not there. So again, we have only 4 guys. And now our basis elements are here. So what we actually proved that if we take algebraic completion of this field, then this set of equations will have 4 solutions, this algebraic completion. Finding explicit solution will be very difficult. It's not as this simple case when everything is explicit, but we know in advance by finding this thing that number of solutions will be 4. Now, since we work with field of fraction, we can have denominators. because chi's are indeterminates, this cannot be equal to 0, because 0 is number, but chi is indeterminate. So this is absolutely fine. But of course, if you do spin chain, we want to put these guys to particular numbers. Well, we are doing physics. And when it puts them to numbers, for almost all values of chi, nothing but happens. Denominators are just regular, but there are some special values of chi when, well, things become problematic. Right? So let's take, for instance, chi 1 equal to 0. This means that this thing blows up, and y cannot be longer expressed in this combination. And moreover, x will satisfy cubic equation, not quartic, but cubic. There will be only 3 solutions for x. Basically, what this means that this Grobner basis like fails to describe this point. The best we can do now is to take this equation, put chi 1 equal to 0, and redo computation. And this is what will be the answer. This will be Grobner basis. So this is the same set as here. Basically, here, if we put chi 2 equal to plus 1, you get the same equations, and it has exactly the same linear monomials, and you actually get exactly the same basis vectors. So basically, what you observe by this, that number of solutions did not change. So this chi equal 1 is actually was fake singularity. It exists only because our reference frames that we have chosen was bad, right? So this becomes some linear dependence here because it's x with a cubic equation. And we have to choose a different basis. That's it. But in different bases, everything is regular and nice, and we still have our solution. So this is kind of good situation when this is a fake singularity. But now, if you put chi 2 equal to -1, then this thing blows up, and now we see that x actually should be equal to 0 at this point, just identically 0. Again, this equation doesn't make sense. Well, actually, they do make sense. We can just boldly put things here. And if you compute Grobner basis accurately, you get this one. And here we say that x is always 0, just like that. But y can be 2 options. And actually, this means that one other way to say that in this polynomial ring, we have to, well, sorry, in this quotient ring, they will have 2 basis vectors only. So this, of course, has only 2 solutions, y equal plus minus I. And what happens that although for generic values of chi, you have 4 solutions, this is kind of a bad point, well, when number of solution changes. And from the point of view of Bethe equations, it's reasonably easy to prove that number of solutions is good one for generic point. It's much harder to, well, then it is some work to prove that this fake singularities can be resolved. And it's even more harder to actually prove that these things do not happen. So Bethe equations, these things do not happen, but I just showed you that this thing can happen for polynomial equations with many variables. Okay, so this is finishes my introduction to polynomial rings. If you have
sorry, another question. So this theorem that number of solutions is dimension of the factor, how complicated is it? Is it related to this Hilbert-Nullstellensatz Satz in some simple way?
We are going to prove it in the second part of my talk. Just so, actually, for the second part of my talk, I will need to prove it, and you will see how complicated. It's very easy, actually.
Sorry, Dima. Still, I'm torturing you with Newton polynomial. Actually, the number of points inside it, sorry, not polynomial, but this Newton rectangle. And here, in particular, for 2 variables, the number of points tells you what is the genus of your algebraic curve, y of x. Is it related somehow with the with your countings?
Well, in a big picture, yes. In the big picture of algebraic geometry, yes. But for particular application to what I'm discussing today, no.
Mm. Especially that if you take more of variables which you have to, then this doesn't make sense, the genus counting this way, probably. Because,
well, right, this Newton polytope that you describe, it's only for 2 variables. Indeed, we have many variables. Yes. Well, there is a statement, I forgot the name, it's, there are 3, I forgot the names, but this is a theorem that mixed volume of Newton polytope is number of solutions of your equations as well. I forgot what is the name. It's called BKK bound. Who is BKK? I don't remember. Well, you can Google it, BKK bound.
Thanks.
So finally, we are coming to like essential part is completeness. So we are going to count dimension of the quotient ring and hence count number of solution to Bethe equations. So let's make a little bit more precise what we are going to do. So this is our spin chain. So we work in the defining representation. So it's one box, one box. And so it's of length L and Hamiltonian, because you consider periodic boundary condition, is invariant action of GLM/n. That means in the tensor product of these boxes, we have to pick irreducible representation, which is described by Young diagram. And Hamiltonian, well, spectrum inside each rep will be like fixed. And therefore, we can focus only highest weight vectors. So the rule of the game will be the following one. We pick our favorite Young diagram. This means we pick the rep that we want to study and restrict to the subspace of all possible highest weight vectors of these reps. There will be many reps of the same shape. I mean, not only one rep of this type, but many. Now, how many? For this, just let me remind that there is a Schur-Weil duality. So there is also a permutation group which acts on the spin chain, and it can permute sides. And this is like they form a dual pair. And so number of different reps, number of reps with the same Young diagram is actually given by dimension of a rep of this guy. And this dimension of this rep, practical thing, is number of standard Young tableau. Okay, so we expect that number of solutions is given by number of standard.
So you're saying like number of states corresponding to a given Young tableau. So all the states are related just by permutation of the sides.
Well, yes. Well, I said
you can map one state to another by permuting the sides.
No. Well, it's a little. No, it's not just permuting sides. When you fix a rep here by Schur-Weil duality, you also fix a rep here.
Is it just the statement that when you have a representation labeled by some Young diagram, then to get all the states, you should fill this diagram with numbers?
Yes, that's right. Yes, that's right. Yes. So a rep is Young diagram, and how the number of ways we can fill it with numbers is number of different reps. Of reps of the same type.
But so you fill following some rules with numbers.
That's right. What are the rules? So we have to fill it from numbers from 1 to L. In this case, there are 10 boxes, so from 1 to 10. And numbers should increase to the right and down. This is called standard Young tableau. Standard Young tableau. So it's French, right? So tableau without X is singular and with X is plural. So this is correct sentence. Right, so this is the rule. You take your shape, you fill it with numbers such that they increase to the right and down, and this all numbers from 1 to length of your spin chain. And how many ways you can fill, this is how many solutions to Bethe equations you should get. Right, and so there is another thing which is quite funny. The fact that it is dual pair, that means that anything which commute with GLM/n should be inside group algebra of permutation group. And that means that Hamiltonian, which commute with GLM/n, is actually inside group algebra. So actually, Hamiltonian has not much to do with GLM/n itself. And so its spectrum should not care about actually this thing, and actually it doesn't. Actually, it's care only it only cares about shape of the Young diagram, and my description will be very explicitly dependent on shape of Young diagrams. There will be no really notion of rank. You're going to see it now. To make this super explicit, I decided to use Q-system on Young diagram as a good Bethe equations. So this is what I'm going to explain now. Okay, so this is our Young diagram. This is irreducible representation of GLM/n that we decided to consider. And so if you introduce indices A and S in this and parameterize lattice in this way, that to each intersection of lines at each node, I will assign one Q function. This Q function is a polynomial, QS is a polynomial of certain degree. what is this degree? It's number of boxes in southeast direction. So in this case, like 6 boxes, so degree is 6. Okay, and for each node, there is exactly one such Q function. Now, this polynomial should satisfy this Plücker type relation. So Wronskian is defined as follows. And so we have to require that this Wronskian is proportional to this product. So it's better to imagine graphics. So Q function is here. Wronskian with Q function here is a product of Q functions at these nodes. Can I ask you, is the graphics clear? Because I will use it quite a lot.
Maybe you could say it again.
Okay, so I take like any plaquette you like this one, for instance. Okay, so this square is this plaquette. Okay, and at each node of the plaquette there will be exactly one Q function. So here is this QAS, right? QAS. Here it will be A plus 1 S plus 1, right? So this circle means Q function at this point. Is it okay now? So Wronskian between these two Q functions.
So the two boxes are the sort of diagonal boxes in the main diagram.
And your Q functions are at vertices.
Diagonal boxes. Why diagonal? Any boxes. Any box.
No, but in the specific example you're giving. So it's the box you pointed to, and then the one that's one down diagonal.
Yes, this one. Yes.
No, but there's two boxes or one box?
The box is fixed. It's only the points which change on the box.
Ah.
Yeah.
Oh, I see.
The box is fixed, right? So this is upper left corner of the box. Okay.
Okay.
So I take this box, this box, only this box. That's it. Okay. And
so the Wronskian is always just for one box.
Only for one box, yes. And the product also for the same one box, but just different corners of the box. Okay, hopefully notation is clear, and so probably I can continue them. All right, so notice that on the boundary...
Excuse me, what do you do on the boundary? Or in principle, it's an infinite relation, set of relations. You can continue this diagram.
No, well, I mean, no, it's not infinite. For when there is no twist, it's actually, there is explicit boundary for it. So that's what I'm going to tell now. So on the boundary, so you only want to write this equation on the boxes of Young diagram. You do not want to write it outside of Young diagram. This is what's called Q system on Young diagram.
Usually Q functions have nothing to do with representations of the group, yes?
They have something to do with the representation of permutation group.
Yeah, but not with the representations of GLN, which you probably use.
Yeah, so this is no. You see, so Q functions has nothing to do, but we restrict it to some subspace, and the degree of these polynomials, like analytic properties of Q functions, have to do with representation.
Just which Q functions
so this
are,
is like
trivial related to the concrete state, but in principle, the whole set of Q function is always the same. Just some of them are die out, right? Is it correct?
That's right. They're all
dependent.
That's right. So if you do not restrict to particular reducible representation, that Q function live in the whole like lower quadrant everywhere. But if you speak a particular representation, that everything outside here will die out. Well, or will be ill-defined. It's a long story. Okay, but
how are they related to the well-known Q functions like this Q and Q tilde, for example? And
this you will see. I mean, I will show you.
Okay.
Yeah. But first, let me finish the rules of the game. So on the boundary, degree of polynomials is 0 because there are no boxes in southeast direction. Okay. So we just said that Q function there is equal to 1 at each point of the boundary. Q function is equal to 1, and well, we do not go beyond the boundary. So it's like terminal point is boundary condition. Q function equal to 1 here. But another boundary condition is this point. It's point 0, 0. So in this 0, 0, I need this Q theta polynomial. So polynomial defined by the homogeneities of my spin chain. This is actually quantization condition. So so the game is the following. We want to find all possible polynomial solution of these Plücker identities subject to this constraint. And the claim, this is like complete. I have correct number of solutions. Okay.
Sorry, in this M's, are this related to these numbers you were showing on the previous slide?
Sure.
So M's
well, yes, it's related, but it will be the very, very one before the last slide of my talk. How it's related? This is definitely related. Yes.
Yeah, just a question. So now you are looking at the twistless case, or
yes,
the twist?
Twistless case. So I can do twisted, but I just do not show it in this talk.
Okay.
Yeah. So twisted, by the way, is simpler. But okay. Right. So at least, so I hope you understood the rules of the game. And now I will give you 4 different parameterizations of this Q system, and you will see connections with things that you know. So the one is just to mention this is a very lazy way to parameterize a system. Well, you just say, okay, all these guys are polynomials, so let's just take these coefficients as parameters. There is no symmetry freedom, so nobody is red. So everybody is important, physically relevant. So this is something nice about this system. And you say, okay, I write all these possible coefficients, all possible relations. It's like lazy way. It's definitely like a super big overdetermined system, but actually it's worked very well for numerics actually. And mathematics.
You might call it democratic as well.
Democratic, yes, good. Lazy on, well, is democratic means lazy? Interesting. But okay, so democratic parameterization. So actually I use it really for numerics. And I have a program which is called Lazy Beta Solver. It works very well. But I mean, of course, to understand things, of course, it's like too much of coefficients to track around for human beings. So we have to do something different. So second one is related to nested Bethe equations, like the one which you learn it the first time you do integrability. So this parameterization I call along Katz-Dymkin path. So this is basically related to the work by Volodya and collaborators. This is kind of incarnation of these ideas to this setup. So, and the first time we proposed this with Christian Marbu when we formulated Q-system diagram. So the goal is the following: you take arbitrary paths that you like from corner when you know Q function is this Q theta, and this path to external boundary of Young diagram. So this is, well, each straight direction is bosonic node of Katz-Dymkin diagram, each turn is fermionic node of Katz-Dymkin diagram. So it's for you to define a Lie algebra that you want to consider. So in this case, I choose this path. That means that I think about this Q system as solving Bethe equation for GL2/3 spin chain. Okay, I told you Lie algebra is irrelevant, but by choosing a path, you can bring it back. And so what I can do, I can only parameterize Q function using this parameterization only on the path. I take only these 4 Q functions. And Q function has a property. Zeros of these guys are beta roots of nested Bethe equations along this path. Okay. So if you want, you can take this path here, from here to here, and then it will be so it will be what? It will be SU5 rational spin chain, completely bosonic, not supersymmetric. And Q function, it will be momentum carrying. So zeros of this Q function will be momentum carrying beta roots, and zeros of these 3 guys will be beta roots at nested levels.
So by specifying the final point, you kind of choose a particular spin chain.
That's right, particular Lie algebra for which one.
Then all passes, they correspond to dualities.
That's right. If these 2 points are fixed, there are many different passes with this fixed beginning and point, and different passes, it's duality transformations between Bethe equations. Yeah.
But then, sorry, I'm a bit confused. So this will be only fermionic dualities, right?
Only fermionic, that's right. There are no bosonic dualities here. Yes.
So your initial example where you had SU2 is not kind of embedded?
This will be parameterization number 3. Yeah. So this is related to nested Bethe equations, not to Wronskian.
So just to clarify one thing before you move on. So so your path currently describes GL2/3. So if I cannot write the Dymkin path for say n/m and get to the boundary, can that Young diagram not appear for that algebra? Or is it?
That's right. So if for instance, you want to consider GL2/2, that 2/2 is inside the Young diagram, then it means that you do not have enough of indices to antisymmetrize and get the right representation. So
Okay.
this guy absent from your spectrum, that's all. Right. So it's important that your algebra should be like on the boundary or like outside. If it's outside, it means a short representation, and you can always reduce it to the boundary. And this is discussed in our paper, how to make reductions. And so, I mean, you can also go far away from the boundary, like here, and big like GL10/10 is possible. The problem is that everything outside of boundary is not excited Bethe nodes of Bethe equations. That's all.
So you are solving not only false solutions, but also false spin chains, right? At the same time. Okay.
All spin chains, yes. All spin chains, indeed.
Dima, some of these functions should be the same as in Hasse diagram, and there are a finite number of them, yes?
That's right. Okay. For Volodya. So basically, you have considered Q function with, okay, for this.
Inside the square here.
So for Volodya, so on the Hasse diagram, we have Q function of this type when A is multi-index and Qj is multi-index. Okay. So this you know, of course. Now, so this is Q function on a Young diagram is equal Qij, where Aj is such that is I don't know how to write it properly. In Pol over Aj, such that A is equal to A, J is equal to S. Well, okay, what I'm trying to say, you consider all Q functions which have the same number of indices, A and J. Okay, so A is multi-index, J is multi-index. I consider Q function which number of indices for Ij is the same, equal S and S. Among all these Q functions, they're all polynomials because we're doing compact representations. Among all of them will be the one, the distinguished one, you have polynomial of the lowest degree. Okay, and this polynomial of the lowest degree is Q function of the Young diagram.
So it's lowest degree polynomial within a given number of indices.
That's right. Yeah, thank you, Kolya. It's very precise formulation what I'm trying to say.
Wait, but S can be more than the rank of this second.
That's right. So this means that you can embed in a spin chain of very big rank, indeed.
So this means that in your Young tableau, you have to single out a square, no? Isn't it?
That means in my Young diagram, if I want to consider Hasse diagram of particular rank, I have to single out the square. In this case, if I want GL2/3, I have to single out only this guy.
Not the square, but
this
rectangle.
Yeah, so if I want GL2/3, that only these guys will belong to Hasse diagram, and this will be some extra bonus.
So those are functions new for me. It's interesting that they somehow relate to the usual Q functions, usual in the old sense, and has a diagram to something which already is the group representation.
Yes. So what you actually do, you can always think about spin chain as embedded to spin chain of bigger rank group. That's all.
Nice.
Okay. Right. So actually, okay. So, but how we are going to solve the system? So we say, okay, we parameterize this guy using this coefficient C, and then we use this identity. Do you see it? Sorry. Do you see this guy here? This formula, do you see it?
Yes.
Okay. So what is written here? We have a polynomial A and B. When you divide polynomial A and B, I have this zoom which I cannot see. Okay. So we divide polynomial A by polynomial B. This is not a Q function. This is quotient of polynomial division. This is remainder of polynomial division. So there is a Euclid algorithm that allows to find quotient and remainder ambiguously as a linear combination. I mean, not linear, polynomial combination of coefficients of n b, or just long division statement. Okay. So basically, what we are doing now, when we have this Q function that are fixed, let's consider this box, for instance. So take this equation on this box, and so these three guys are known. So this guy is known, this guy is known, and this guy is known, this guy is known, and this guy is known, but this is not known. Okay. So we know 3, but not 1. So this guy is the ratio of Wronskian divided by this guy. I hope it's clear. So we employ these 3 guys as known on the right-hand side and compute this guy. If not clear, please ask me. Now, so for arbitrary polynomials, when c's are not fixed to be numbers, but arbitrary variables, there is no reason that this polynomial division has 0 remainder. However, we can compute it quotient. It's just algebraic operation. And we know that when Bethe equation satisfied remainder is 0, that we know that this guy is actually quotient of this division. That's how we compute this guy, is a quotient of these 2 polynomials. Okay, but what about remainder? Remainder should vanish if we have physical solutions. And so we introduce for each, when we do this computation, we compute quotient to find this node parameterized by this coefficient, and we compute remainder, and condition that it's equal to 0 is good Bethe equations, right? So this is a way to find polynomial solution to this system. And we do it recursively for all these guys. So to the left of Katz-Dennking path, we go in this direction. To the right of Katz-Dennking path, we go this direction. So we compute all possible quotients and collect, like so and trip in Mathematica, right? And collect all possible remainders, and then ask Mathematica to solve for these 0 remainder conditions your system. So this is like super efficient compared to normal methods. With Christian, we managed to solve analytically SU2 spin chain of length 12. And we managed to find, using this method, first 8,000 states of n=4 supernormal spectrum using this method. Okay. So this is, I mentioned this to relate to Bethe equation, nested Bethe equations, and like to, it's historically is important parameterization. Okay. So, but we are not going to use it parameterization for our purposes. So the third one is bosonized parameterization. Okay, this is adaptation of ideas of this work to the setup, right? And this is the one we actually explain in more detail in our last paper with Dmitry and Sebastian. So, how this is bosonized parameterization? What it is? So first of all, I'll remind you that we have a Young diagram. So Young diagram is integer partition given by these integers. So lambda1, lambda2, etc. are lengths of rows. And so we introduce functions QA. There are as many Q functions QA as the height of this Young diagram. And degree of this Q function, they're all polynomial, everybody is polynomial. So degree of these polynomials is shifted weight, like standard definition of shifted weight for representation theory. And also introduced bosonized Q function BS, whose degree is new as, so there are as many of them as widths of Young diagram, and their degree is essentially negative of shifted weight with some adjustment. You do not really need to understand this formula much. You can do it graphically. You actually like do Manhattan path, and you compute distance over Manhattan paths. You just populate guys with numbers from 1 to the last number, from 0 to last number. So all green guys are precisely degrees of B, and all orange guys are precisely degrees of Q. Okay. And so what you can show that our Q functions on Young diagram is given by this Wronskian. So let me explain what this Wronskian actually do. Suppose you want to compute Q function at this point. So you consider all B's in vertical directions, there's 3 of them, and put them here to Wronskian. And you consider all Q's in horizontal direction, put them here, right? Well, and this is like rule for each node. And well, this is a way to solve Q system. Okay. Now, again, so when you have a Wronskian, we can make a linear combination of functions, and some coefficients can be killed. If you look carefully here, like this B has degree 4, but monomials of degree 3, 2, 1, 0 appear in Wronskian. And so it's only leading coefficient of B which actually is relevant for computation. And actually, whatever Q functions you're going to choose, only leading coefficient of B will be ever relevant. So actually, by symmetry, we can always fix to B just its leading coefficient plus nothing else, because nothing else will never contribute to this Wronskian. For Q function, it's not the case though. Situation is not symmetric. So here, for this guy, indeed, if it's degree 6, so degree 4, 3, 2, 1, 0 will cancel away. But if you consider this Q function on this boundary, then actually there will be no B functions at all. And it means for this guy, only we can subtract Q functions of lower degree. So if you want to compute, do you see my mouse?
Yes.
Yes. Okay. So if you want to consider this Q function is function of degree 6, degree 3 and 2 will be subtracted, but there will be no B function. So all other coefficients are important for it. So when we parameterize Q function by this polynomial, we have blue, which is important physically, guys, and red coefficients, which have this labeling, should be taken away. They're not physical. So this is like parameterization. So B just like auxiliary, guys, Q are physically important. And so this is a formula. And now if you compute Q00, the one which is quantization condition, then it's Wronskian of all QAs, of all of them. And this is actually Wronskian Bethe equation for bosonic system. So this is exactly what we did at the very beginning. So for SU2 case, we have two Q functions, Q eq tilde, equal to this. And so basically it corresponds to a Young diagram of height 2. For GL2, you have Young diagrams of height 2 only. Right? And so when there are only two Q functions, it will be Q and Q tilde from our GL2 example. But if you have SUH system, you have to write H Q function like this. And this is, by the way, Wronskian Bethe equations that we used in the paper and make superestimated equation of them.
Sorry, so those Q's and B's living on the boundary, those are not the same as Q with two indices, right? This is new.
Well, actually, they do not live on the boundary. They live at this, QA live here. If you think about projection of Hasse diagram, QA live here and BS live here. This boundary is only like their degrees to compute. So you have to imagine, well, for you and like for no people who knew the story, you have to consider m/n when it's here, like m/n. Okay, I hope it's clear. You have to consider big rectangle.
Mm-hmm.
And then you have QA/0, and this is bosonized. Well, it will be QS, no, Q full set /S, right?
Mm.
Yeah.
So QA is QA/full set, and BS is Q empties. No, full what?
No, I think QA is a QA is QA/empty set, and BS is Q full set /S.
Okay.
Like this.
So, Dima, essentially, if I want to take the Q function, I'm sliding along this boundary, right? So, and this regardless quantization condition. So the upper one for Q not is universal. But your Wronskian Bethe equations, how do they change if you choose different places, or is there a dependence?
No, sorry. You see, I need to consider this Wronskian only here because here
sure.
So I have only one Wronskian Bethe equation. I cannot choose like this point. Is it your question? Because this point is
yes. What if you take arbitrary point? What is the dependence? Is this universal? Am I taking this correct?
Well, this formula is true for any AS, right?
Sure.
Okay. I took A and S equal to 0 because here this Q function is fixed. It's quantization condition.
Yes.
Well, and this is an equation. So I'm not sure that I understand question.
So Dima, if you can pick some time for a little break because we're like boiling.
Okay. All right. So.
I mean, I think it'll be okay if we go over the expected time a little bit, but probably a little break might help.
Okay.
Yeah, just so is it natural now? So what's the point of the slide to summarize? So you relate this Q with two indices to this Q, your Qs with AS with the Qs with one index which Volody likes.
That's right. So I wanted to relate Kisismayan diagram to this Wronskian Bethe equations that some of you know.
And so you know, the point is to link it to your first slide where you consider SU2 and you have bosonic duality.
That's right. I want to explain this, yes.
Mm-hmm.
Yes.
But in principle, you are saying you don't need actually to go back into this.
Yes.
You can just leave on this diagram and use this Q with 2 indices which you introduced.
Yes, I can.
And
yes.
impose that all this remainders remained at 0, right?
Yes.
All right. So what's next slide? Maybe let's see if we can absorb.
I think, sorry, Dima, just if you can back to the previous one. These dualities in the previous slide, one more, yeah. You have chosen some particular placeau. I want to take the Q function, and these dualities they appear in equivalent way as for different roots I'm taking in a chosen placeau.
I do not understand the question.
I mean, how do you define the
dualities?
Dualities. Yeah, so you have chosen placeau and you are going along different routes, and you must be having dualities to relate them. For those routes to be to find an equivalent result, right?
Yes.
For different paths, you mean? From one
yes.
From the top point to a fixed point on the boundary.
Yes. For example, here you have right, and here they must be accompanied with dualities if I'm choosing the different path. Like you say in the rectangle, I'm choosing the lower path.
Okay, so you can do here, 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 and down. Yes, we can do this, and that means instead of choosing this guy.
Yeah, but in the next
guy, I choose this guy. Yes.
Okay. But so the same rules apply in the next picture, like what you show, right?
Oh
no.
Well, the next picture is not related to the Kasdankin path at all.
Yeah, but then how do you relate this? How does it relate between this passes and the multi-index labels that you have for QA and BS?
This picture doesn't have passes. They don't have passes.
So you are just
AS.
Okay, you have expression for Q
equations. You need to pick a path, right? And then Q functions along this path will be this beta roots appearing in your equation.
That's right.
Here on relates this universal quantities QAS, which would appear in all possible.
Yeah, exactly. But so is there a direct relation to the Q function of these quantities to the index formalism you use? So you have expression for the Q function, some generic expression in terms of the Wronskian, right? And which you do the shift along the A's and S's.
Why shift? I don't understand the word.
I mean, no. I mean, you are going along A's and S's to find a particular QAS, right?
Well, I do not go somewhere. I just pick A that I like.
Yeah, sure. But I'm starting. So you start with your particularly chosen quantization condition, which you define, like you say, which defines essentially the Wronskian Bethe equations.
Yes.
So I think this question is probably related to how this is this A and S they relate to the conventional multi-indices.
Well, this I explained here, right? So Q multi Q is minimal polynomial between Q function with the same number of indices. This is.
But then you must be having this invariance. Right. Okay. So you do not consider any passes. Okay.
Well, in this parameterization, no.
Yes.
Yeah. So I showed you like like 3 different options so far. You can just say, okay, I want everybody democratically. I want to choose a path and make 0 Riemann condition, or I can do bosonization or parameterization. I will parameterize using this coefficient.
Yes, and they are not related among themselves, right? This approach.
No, they're of course related. They define completely isomorphic beta algebras. They are polynomial.
No, at the level of algebras, of course. But okay, I wanted to see beyond these expressions, I'm not seeing any dualities or something, right?
No, this relation doesn't have any dualities. No.
Sure. Okay, good.
Dima, could you please repeat the definition of B?
Well, it's just postulated here. I do not want to link to something else, otherwise we will go forever.
No, but
No, B in terms of our notations is like as he said, Q full set and then one index.
Q full set slash S is B in our notation. Yes.
So roughly speaking, Q's are Q's and B's are P's.
I see.
B's are P's and Q's are Q's.
Mm-hmm. I see.
Well, Q's are P's and B's are Q's. Yes.
Yeah, simpler.
Perhaps this is a good point to take a 5 or 10 minute break.
Very good for me, but I'm not sure.
No, but I mean, you can use it as a definition. I mean, it's hard to link to.
Yeah. So should we break? Have a break now. So let's say until what? Until 20 past.
Probably, yeah.
Right, coffee break, everyone. See you later. Or tea. Resume. Please.
Okay, so I gave you 3 different parameterizations. So lazy was just to tell that it exists. 2 was number 2 related to conventional nested Bethe equations. 3 related to Wronskian Bethe equations. And this was done so you have connections to what you know. Okay. Now I give you parameterization number 4, which is new. And it doesn't connect to what you know, it's something new. Well, okay, this is here. And I call it native parameterization to Young diagram. Okay. In a sense, it's very democratic, but also quite economical. So the idea is kind of interesting. So basically, if you think about this one, we knew 3 Q functions, we want to find this one, okay? The new idea is to, if you know these 3 Q functions, to find this one. So we start from this boundary where Q function is equal to 1 and go up in this direction, okay? So for instance, take this plaquette and write our Polynomial identity there. And recursively, we say we know these 3 guys. So these 3 guys we know because it's by recursion we know it before, and we want to find this one. Okay.
So this will contain some integration constant.
Exactly. So this is what we call it will contain integration constant, and then why it's non-trivial. So we call this type of equation sportive equation because it requires some exercise to be solved. Yeah. So
like my sportive car. Yeah.
Okay. But okay, let's for the moment solve it formally. Basically, plus and minus means shift by h bar over 2. So this Q functions depends on u, and u shifted by minus h bar over 2. Then there is shift operator, minus opposite. So I mean, this is just rewriting this Wronskian, that's it. And this is equal to this combination. So formal solution to this is given, so this function that we want equal to this. So this is this ratio, and this inversion of this formal operator. Now, we can make formal series. It's actually like very close to generating function for Bernoulli coefficients. There will be one integration and derivatives. So what we can do, we can write all the guys are polynomials, and we can do 1 over u expansion. So a non-trivial statement, then if these 3 guys obtained by this procedure from like recursively, then the result is actually a polynomial. So all the negative powers of u actually will magically cancel out. I mean, that's a theorem. Okay? So therefore, what you can do is, well, you can put it on Mathematica, make like Taylor expansion around u infinity. And this is like, again, you can do. It's a very simple code. And you say, okay, I care only about positive coefficients. Then it will be like finite computation and give you polynomial result. And all negative degrees will cancel anyway, so I don't care about them. They will cancel identically. There is no zero Riemann condition, no Bethe equation, just say cancel identically. Okay. Of course, there will be one integration, and this is an integration constant. And so what at the end you get the following answer. So QAS, this one, will be QAS 0 when integration constant is 0 plus integration constant times this guy, all right? And so by solving this, this equation, we get one new parameter per each integration. And so because we did it as many times as number of boxes, we have exactly as many parameters as number of boxes we diagram. Moreover, each parameter is precisely associated with the box.
So you're saying start from identities at the boundary. At each step you gain one integration constant, and when you reach the corner, you impose it to be theta.
That's right, yes. Yeah, so just I have to say that originally this idea was due to Sebastian Laurent. Well, and now we start to become, we discussed a lot with him this about 3 years ago, and finally starting to be useful. So, I mean, it was definitely very interesting for a long time. Now it's something more interesting starting to happen with it. Yes, and it's, by the way, not a part of our paper. It's like a nice thing to speak with you here on the talk.
Excuse me, so you prefer to expand in derivatives and not in the shifts?
That's right. It's like Euler-Maclaurin, like.
Why any different for this statement of polynomial?
No, it's just a way to effectively compute the answer, right? It's because you know that the answer is a polynomial. This expansion gives you answer in finite number of steps.
And if you have shifts, why?
You have infinite sums. You have to.
Yeah. That's true. That's nice. Mm-hmm.
Right. So basically, by doing this, starting from identity integrating L times, we get constant for each box, and eventually you get Q00 as some polynomial in U, of course, but also in this coefficients of integrations, and it should be equal to quantization conditions. And this is what I will call Young-Wronskian map from this integration coefficients to this polynomial. And if we kind of focus on coefficients, then we got what we should be called Wronskian Bethe equations again. So it's not the same equations as these Wronskian Bethe equations, but they're equivalent. You can show that they're like strictly equivalent in mathematical sense. But they're also kind of very native to Young diagram picture. And this is the one which we are going to use to count number of solutions. So finally, we are arriving to counting, and this is what I actually promised. So we have Wronskian Bethe equations using Young-Wronskian map, right? This coefficient C parameterized Q functions as integration constant. There is constant 1 per each box of the Young diagram. Now, the goal is to compute a quotient ring omega and, well, count the dimension. So I remind you that we do this exercise while in general position of things are nice, we can have troubles at different points. And of course, the whole game is to prove that these troubles do not appear, or like how to deal with them. So we did it in different ways. In the paper, there is like a pedestrian way in appendix and like a more high-level way in the main text. And explain high-level way, basically stated, because it's like a really nice conception. So what we were able to prove, and this was actually the bottleneck of the paper, as now we understand, that we can prove that Wronskian algebra is a free C-chi model. So let me explain what does it mean. So first of all, what is Wronskian algebra? The Wronskian algebra is this quotient, but notice a difference. This is here we have a field of fractions, and here we work over polynomial ring. So we no longer allow to divide by polynomials in chi. This is how Wronskian algebra is defined, but otherwise, like it's the same thing. Okay, and the theorem itself says, I mean, I just explained it in words, that there exists a basis in this algebra it's very non-trivial basis, and we cannot find it explicitly. But the terms about existence, it exists, such that any element of the Wronskian algebra can be represented in these combinations where R are polynomials in chi, not rational. I mean, when it was a field of fraction, of course, this basis existed, and this was rational guys. But the point is that there exists very special basis when these guys are polynomials. And if they're polynomials, putting chi to any numerical value that you like is not a problem. You can do it, okay? And moreover, you can easily prove that if it's a basis for chi being indeterminate, it will remain a basis when chi becomes any explicit number that you like, okay? So I will not explain you proof, like the key idea to prove that C are bounded if chi are finite numbers, and then reduce to prove to the Quillen-Suslin theorem. So Quillen-Suslin theorem is a fundamental result of algebraic geometry. So it was conjectured by Serre in 50s and proven by Quillen and Suslin 20 years later. And Quillen, in part for this proof, was awarded a Fields Medal. So it's quite a non-trivial statement. And actually, I think that there should be much more easy way. I mean, we have very simple equations, and there should be much more easy proof, but we could not find it and use this fundamental theorem. So to realize that we can, that it is true, this theorem is useful, true, and to prove it, it was one of the two bottlenecks of actually doing the paper. Okay, but the moment we prove this, things become super simple. And I mean, everybody like in the audience did it many times in his life. We are going to do partition function now from this moment. So finally, we count the number of solutions using Hilbert series. So Hilbert series is like a fancy name, but it's the same as character, the same thing as index, the same thing as partition function. We count dimension using some weight. That's it. So it's just dimension analysis from now on. So I actually will finish here the whole proof now. So assign degree to coefficients C and chi. So what is HAS? HAS is a so-called hook length. So why assign this degree? So notice that everybody is a polynomial in U. And so if we assign degree, I mean, if you measure U in meters, then everybody become dimensionful. And so I remind you that this polynomial, let's take, for instance, this point, AS is 0, 0, just for clarity. So we speak about C11 now. So if AS, AS is degree of polynomial is number of boxes in south.
So just, sorry to jump in front. So H would be a number of steps you need to get this to this point, right? When you like go from the boundaries and...
No.
No?
I don't think so, no. No, it's not true. So degree of polynomial of Q is a number of these boxes. Degree of polynomial A plus 1 S1, which is here, is number of boxes below this line. And degree of C is the difference between numbers, so number of these boxes. Okay, this is what's called hook length. Okay, so is it clear now?
Yeah.
Okay. So this is degree of C, just dimensional analysis of this formula. And degree of chi is chi alpha is equal to alpha. Just to remind you that chi alpha is alpha's elementary symmetric polynomials in thetas, and degree of theta is of course equal to 1. It's obvious, and chi, well, it's also clear. So this is very natural gradings we can assign to a system. And so you can do what is called filtration now. Well, I mean, just stay with me. It's actually very simple. So you say, okay, W2 is a subspace of quotient ring, which consists of all guys whose degree doesn't exceed 2, right? W1 guys whose degree doesn't exceed 1. W0 doesn't exceed 0, so it means only constant here. So this is called filtration, it's embedding of stuff. And grading is compatible if this is true, and this is true because everybody is polynomial in new equation, so it's not difficult to show. And character is counting dimension of homogeneous spaces, basically. There's some quotient story here. Well, you can basically think about this, it's just minus, but basically this is like homogeneous space here. So character or Hilbert series is just partition function where coefficient is dimension of homogeneous spaces with respect to this gradient times some fugacity guy. Okay, this is character. So we are going to compute this character now. And yeah, so this is actually simple. So this Wronskian quotient ring is actually over complex numbers isomorphic to free polynomial algebra of Cs only. Well, indeed. So here in this definition, chi and C play a completely symmetric role in numerator. But the point that denominator tells that chi can be always solved in terms of C easily. Well, we want to solve C in terms of chi, this is Bethe equations, but if you want to do the opposite, solve chi in terms of C, it's easy. So every time you see chi, you can replace it with this combination, and the denominator disappears, you get this condition. But computing character of this space is super easy. Well, this is the answer, because, well, each term of the product is generation of all possible powers of CAS, and this is a character. So hope this statement is clear. Okay, and so what is left? We also have to compute character of field of coefficients. This is this one. So alpha is degree of chi, and there is L chi's. Yeah. Okay, and to compute dimension, we have to take all possible elements of W, of omega, divide by all these coefficients as an arbitrary polynomial. This is the point of being free. You can just boldly divide like in counting and set equal to 1. Well, I don't know, L'Hopital rule or whatever you like to get this answer. And so this is a famous Hooke formula. Which is known to count number of standard tableau. I must to say something more. This is actually some polynomial. So this is not like infinite series. Actually, they divide one by another, become just a polynomial. And it's also very famous. It's so-called Koska-Fulke polynomial. It's important combinatorial object. And so actually, we did not count only dimension of the Wronskian algebra. We actually count some type of character which describes in more detail this algebra, and wonder how it can be used for something else. But anyway, so this is a proof. Dimension of the Wronskian algebra over C chi is this chi. Because it's free model, chi can be put any number you want, no problem, because everybody is a polynomial. So algebraic number of solutions of Bethe equations for any value of inhomogeneities is equal to number of standard tableaus. And this completes proof of completeness. Okay, so I'm giving you a summary. So summary, nested Bethe equation should be replaced by Wronskian Bethe equations. It can be done in many different ways. I show you several different ways to do it, like I say 4 ways I showed you. And the one which you use for counting was replace this nested Bethe equation with Cartan matrix, etc., to this Wronskian condition using Jan-Wronski map. So second statement that Wronskian Bethe equation depend only on Young diagram, but not on the rank of JLM/algebra. So indeed, as Kole said, we are not finding all solutions. We also solving all spin chains at once. We don't really care about what is M as N here, and in particular, it can be bosonic. So we introduce Young diagram natural parameterization. So again, so this is not a part of the paper itself. In paper, it is slightly different thing, but it's a possible way and very symmetric. So that's why I wanted to present it. And so define Wronskian algebra and prove that it is free C-chi model. So important that I explain you already that number of solutions is then for any numerical chi bar. So chi bar, it means number, chi is indeterminate without bar. And finally, compute number of solutions, which is Hooke formula. So this is finishes like first part of my talk, and I think I can take away most part of the second talk, but I still want 10 minutes more if you're okay, for something that you would definitely appreciate.
Sure.
Yeah.
Yeah,
So,
time as well, yeah.
Oh, sure.
Okay, so any questions about this one? So this finishes computing number of solutions to Bethe equations.
Yeah, so but by Bethe equation, you actually understand instead of beta roots, you have this parameterization terms of integration constants, right? So if this one is complete, whether another one is complete, it's not totally the same, right?
Okay, I mean, so Wronskian Bethe equations in terms of Wronskian determinant, like with Q and Q tilde, is absolutely equivalent to these ones. I mean, you can prove that it is the same Wronskian algebra. They're isomorphic as algebras. So they're, of course, complete. So anything that I describe using Young diagrams, all four parameterizations, they are isomorphic as algebras, so they're all complete. And what I'm saying that I know
but they're all better than Bethe equations, right?
Well, they're all equivalent to one another and better than Bethe equations, yes.
But like for Bethe equation, it's probably not true that there are as many solutions as you need for any thetas you imagine, right? There will be this bad configurations.
Right, but then, right, so if you have bad configurations for Bethe equations, well, then you have to regularize it, solve it, and then take limit and say, okay, this is how I do it.
But in your case, as far as I understood, you don't need to rely on that, right? You just take any thetas you like, and that counts your number of solutions. So in this parameterization, in terms of C's rather than in terms of beta roots, it's really for any configuration of thetas and twists, right?
That's right. It's always correct number indeed. Yes.
So then the question is, for which of this many reformulation of beta and that equations you have the completeness proof of in the situation when no matter what happens with the parameters?
No, okay, one moment. So I show you four formulations. They are all equivalent. Okay, I can prove that they are all completely equivalent. I have proof for one, I get all of them. Is it your question?
Well, but then it's contradicts the statement that for beta and that equations themselves, this theorem doesn't hold, right? Because there are counterexamples.
No, but again, so what is counter? No, I mean, no, okay. So let's go here maybe. Okay, solve in your favorite way using good Bethe equations.
Yeah, good. Okay, good. I can
take a path, and the statement that's zeros of this path I mean, zeros of Q function of this path are beta roots of nets of Bethe equations.
Yeah, once you have solution in terms of this Q's with two indices, say, of course, you can create solution of beta on that equation. Right?
Yeah. So, but some of the solutions will be of type 0 divided by 0.
Yes.
But then, okay, you say, okay, this is 0 by 0, but still it's the one that we have to consider. Yeah.
I think you're just providing let's say a deformation or a resolution or something that in those cases where things blow up, right?
Yes, yes, yes. And it's possible the beta root coincides. There are some situations with beta root coincide, and this will be still a good physical solution, and we still have to claim that it's a solution of Bethe equation that you have to keep. Yes.
Yeah, so which of those four formulations will give you a good definition of physical solution, in other words?
No, okay, once more. Four formulation is completely equivalent. I mean, there is no like something to do. I mean, so from
like if I start from Bethe equation, sometimes I won't be able to say whether it's a good solution or not, because I get 0 over 0 or beta roots equal. But with extended understanding, you can actually resolve these cases, right? And understand which are physical.
Yes, yes, yes. So again,
I'm asking, so which of these four formulations are more complete than beta and that? Beta and that obviously is not complete.
It sounds like this YW, the last one that you gave, is slightly better because you don't have any of these issues that the normal Bethe equations have.
No, okay. First of all, I do not like which of four, because all four are equivalent. I mean, this is mathematical statements. They're all equivalent. I can polynomially...
Except at funny points.
No, at all points.
Well, but again, so then there is something wrong because your theorem tells there is always that number of solutions, whereas if I start from beta on that equation, I will sometimes fail to find all solutions I want. I don't introduce theta's. And
okay. So there is some confusion. My 4 formulations that I showed you, none of them include nested beta equations. I say that they do not. I say that zeros of this guy are solutions to nested beta equations. I don't say that I'm going to use nested beta equations.
So they're all a la Wronskian, right?
They're all a la Wronskian, yes.
So whenever there is Wronskian, everything is good. That's the message today.
Yes, yes.
Okay, thanks.
Dima, what happens when you Q deform? What changes?
Well, what changes in the proof, I do not know. So I do not know like how to answer a question. So I honestly did not study like for Q system for Q deform case. I do not have mathematics. I mean, of course, kind of have some intuition what should be done, but I never did like explicit work on this XXZ story.
But isn't that exactly the same? Just instead of polynomial, there's some trigonometric kind of.
Well, that's
for generic Q probably, but if you take Q to be root of unity, then probably something needs to be modified a bit more subtly.
Yeah.
Yeah. Well, so I do not have mathematically precise statement. Of course, I assume that everything should be the same, except we have to consider like Laurent polynomials of exponential of vector parameter, and things will work. But yeah, so I do not have any terms about this.
You explained me, or not only me, but you explained at some point that there is a way to deform by Q deformation to go to the crystal basis where the beta roots in a sense is a good parameterization.
Yes. But I did not. I know this fact as a fact. I did not analyze it. Yeah. Well, I can.
Most of the time, beta roots are good parameterization. It's just in a very fine-tuned cases when they become a bit dodgy. Right?
Yeah. So in general position, beta equations like nested beta equations completely fine. Yes. In general position, it's indeed the case.
All right, so you wanted 10 more minutes. Is that what you wanted them for, or?
Yes. So let me show you. So yeah, you see, I show you how to solve beta equations, but we need also to prove that these solutions actually eigen values of Baxter Q operators. Okay, so this I'm not going to do, but just I'm telling you that it's another big business. So we know that eigenvalues of Baxter Q operators solve Wronskian beta equations, but we want to show the opposite, that each solution is actually eigenvalue. And there is some subtleties, and this is what I wanted to discuss, but this I will skip. So just, I wanted to discuss this stuff. This is kind of explains you the proof a little bit, and well, there's a lot of things to discuss. It's like 1 hour more, and this we will not do today. There is proof of this theorem, which again, I will not have time to explain. There is funny Jordan-Chevalier decomposition with exact sequences. So all this I skip, okay? Probably I have to mention that the proof, first, basically the main idea of some part of a proof was due to these gentlemen, we have to update it. But there's also some new things we have to do. But interesting thing that there is degenerative Hecke algebra that appear. So it was quite fun too. And this is actually generator of degenerative Hecke algebra. So this is just normal R matrix in this channel, this physical spaces. Sorry, this is two physical spaces auxiliary. So usually in Baxter written in different channel, but in this channel, this is R matrix. And if we add this guy here, this is what is generator of this Hecke algebra. And this is Young centralizer. Yeah, so it's actually a very beautiful story, which I will skip. But the thing I want to tell you, and which is very related, is how to label with standard tableau. Okay. The thing after you prove that Bethe algebra. So what we can prove the Bethe algebra. Okay, at least let me tell you the statement. It's important. So Bethe algebra is isomorphic to Wronskian algebra if inhomogeneity satisfies this equation. Okay, constraint. So what is this constraint? They should not differ by h bar if alpha bigger than beta. So they can be differ by h bar if alpha smaller than beta. So alpha is positioned in a spin chain. Okay, that's very funny. So this condition of the fact that Youngian representation is cyclic. And to know that there is absolutely no restriction on value of symmetric combination of chi. So there is no restriction on beta equations themselves. There's only restricted how I realize spin chain, which inhomogeneity put in which order. And if this is true, then Bethe algebra is isomorphic to Wronskian algebra. And Wronskian algebra is this omega, which is quotient ring. Okay, there is some statement, and this important consequence that Bethe algebra, because of this isomorphism, Bethe algebra will have simple spectrum every time it is diagonalizable. Right, that means that if inhomogeneities are real, we know the Bethe algebra is invariant under Hermitian conjugation, then it means it should be diagonalizable, and hence it has simple spectrum. So that means that if you change your theta's along the real line, you can never cross two solutions of Bethe equation, just impossible. So there's a complete, like they're analytically connected with no ambiguity between. So you can start from point theta equal to 0, take your favorite solution and send it to this limit when thetas are far apart with exponential separation. Okay. And the point that because of this statement, it's an ambiguous procedure. You will never you will know always which solution is which. But in this region, it is possible to solve or label solution, to solve explicitly Bethe equations and label them by some tableau. And some tableau, I remind you, this is filling with numbers of your Young diagram. So how it works? So you remember this Q-system Young diagram? So, so 10 is the biggest number. So this means theta 10 is like the biggest theta when lambda goes to infinity. So what happens when theta 10 goes to infinity? What happens that in this green rectangle, precisely one beta root becomes of order of theta n with some known coefficient. Only one. Outside of this rectangle, all beta roots stay finite. By beta root, I mean 0 of Q function. And moreover, Q prime, which like Q function without this big factor, satisfy Q system with one box left. So next number is 9. That means that for these 5 guys, precisely one beta root will have proportionality to n minus 1. And so Q2 double prime also satisfy Q system on Young diagram with 9 disappeared. So we go little by little, make it smaller, smaller, smaller until nothing is left. And this is how we get standard Young tableau. So the idea is the following, that beta roots stick to inhomogeneities and they are big. This means U is equal to proportional to theta, means stick to inhomogeneity. But the way how they stick depends on controlled by choice of standard Young tableau. It's not arbitrary way.
Yeah, so I mean, it's like plus minus I, or like depending on this number or something like that. So it's theta with some shift, no?
No, well, in this limit, shift is irrelevant, right? I mean, lambda is so big that it's like out of scale. Yeah.
So what you mean, the proportionality coefficient?
No, when the word stick means that they're proportional to theta, right? By the way, all beta roots become real in this limit. There is no complex beta root left. So stick means that proportional to theta when theta is large, parametrically large. Just to know, this is explicit formula. So if you give tableau tau, then well, explicit coefficient using hook length of this D.
So there is a question in the comments. You know,
yes, I do not see
theta
L. What's the question?
Theta n is the same as theta L?
Oh, yeah, theta n defined. Yeah, sorry, yes, it's theta L, yes, theta L, yes. N is L the same thing, sorry, it's just old slide. Yeah. Okay, so so basically what we are doing, how to get this solution. We choose like the diagrams that you like, and you do lazy parameterization of Q functions, let's say, and you solve in this lambda to infinity regime as a seed, and then you just iterate in Mathematica. So let me show you. So when lambda is very, very large, like 4 is large enough, so these small dots, hope you can see, small dots are in homogeneities in logarithmic scale, in logarithmic plot. You can see it here. And so these are beta roots. And now we slowly iterate lambda to 1 when all homogeneities become equal. And so beta roots deform, 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 deform. Well, and eventually homogeneities becomes all equal to 0, so homogeneous spin chain, and this is a solution. Okay. And this works perfectly well until length equal to 20. We can find any solution you like. And so this is a particular example. So we took this diagram of length equal 18 spin chain, just some young diagram or young tableau. This is a solution. We decided to pick up, just to tell you what the solution looks like to show you a plot. We find, of course, we know also Q functions, but we choose Katz-Dennken path just vertical. This means SU4 spin chain. We have momentum carrying beta root. So blue dots are momentum carrying beta roots. Green is in first nested level and red second nested level. There are 2 second nested level beta roots for green and how many? 10 blue. So this is a solution. Yeah. So now, why I wanted really to tell about this, because if you notice, they form this stringish configuration. So you see these 3 guys form nearly a perfect string. So beta roots displaced by 1. This is strings of length 2 here. This is another strings of length 3. And there are also strings on the less perfect strings of the nested levels. Okay. So we get this famous string hypothesis approximation. But again, so this is exact, everything here, like, well, it's numerical, but it's like exactly justified. We know that solution cannot intersect, and solution at infinity is proved to be labeled by Young tableaus, and we just make numerical iteration and keep step very small to not have troubles. It's completely controlled. So there is no approximations here at all, except it's numerical solution, but it's like very high precision numerics. Now, when people did string hypothesis, they just did not say that beta roots parameterized by strings. They actually make like very specific mode numbers analysis. They formulated what's called rigged configurations. So this is a rigged configuration. And then how they actually proved completeness assuming string hypothesis, say, okay, all rigged, I will tell what rigged configuration in a moment, but they say, okay, assume string hypothesis is true, then we can label everything by rigged configurations, and they found bijection between rigged configuration, and this is an algorithm which biject rigged configuration to standard Young tableau. Okay, this is called Kirillov-Reshetikhin bijection. So what is rigged configuration? Well, this is 3 pictures because it's SU4, so it's like rank 3 algebra. So this is number of boxes is 10. I hopefully 10, right? 10. So this is exact number of boxes equal to number of beta roots. And so this means that this one string of length 3, another string of length 3, string of length 2, 2 strings of length 1. Then on the first nested level, there are 2 strings of length 2, and the third nested level, 1 string of length 2. Okay, these numbers means number of holes for corresponding string configuration. And this numbers is called rigging, and this is number of holes to the right of a string. Okay, so now if you look at this picture and compare to this picture, you see remarkable similarity. So we have one string of length 3, another string of length 3, strings of length 2, and also it's true for nested level, but of course precision will drop down the more you go in nestings. Okay, so again, so this bijection is combinatorial fact. This is how they proved completeness assuming string hypothesis. Okay, our bijection between solution and Young tableau is proven fact that when lambda goes to infinity, we can label by standard Young tableaus. The fact that this picture coincides with this picture is basically a surprise to us. but we like make numerical analysis and continue making it now. And so far we make precise, like it's matches very nicely. And basically you see these numbers here is how many holes on the left. We actually can change these numbers using bijection, change our tableau and generate a solution. And this string basically will move. And that's what really get. And so we actually conjecture the following thing, which I would call exact meaning of string hypothesis. So solution to Wronskian Bethe equation labeled by standard tableau, the continuation from lambda to infinity limit, the one that I explained you how we do, coincide with solution approximated by rigged configurations obtained using KKR bijection. Okay,
so could I ask here?
Yes.
So I was under the impression once I don't know, I checked something. If you just take theta's to be large, but not like huge in comparison to each other, just much bigger than I.
Yes.
Or 1. Then beta roots, they will kind of also stack next to the inhomogeneities, and essentially your spin chain kind of decomposes into several one-dimensional.
Yeah, that's absolutely right. That's exactly.
At each theta, you can probably find all this type of strings, right? Because the beta roots will be separated with respect to theta I by some multiple of like I over 2. Then
No,
maybe you can match it with this counting of strings there.
No, I mean, so counting matches. I mean, nobody says that counting doesn't match. Counting matches perfectly, right? The point that it is also qualitatively matches, you see?
Yeah, so in this regime, they will be like literally, they will literally coincide if you just take all thetas large, but not much larger one than another.
No, but then the regime that you're speaking, there is no string hypothesis, no string left, you see? I mean, all strings, look here. So when thetas are all equal, there are strings, but what happens when theta becoming large? I mean, like not necessarily big log, but like bigger, okay? So beta roots start colliding and like there are no strings like as objects. You see, strings become smaller and smaller, and eventually when theta far away from us, everybody is real. There are no string configurations at all.
Okay, we will discuss later, but it's a bit different limit what I'm proposing. It's just having all differences between thetas large, but of the same order.
It's Gaussian model, right? I mean,
and there you should be able to do one by one, probably match with this counting with this funny diagrams of.
Well, okay. I mean, we can speak about this. So I'm just saying that all thetas equal to 0. There is the best. The best approximation to strings without Q deformation is when thetas are 0, and I just qualitatively showed. Yeah. So of course you can enhance strings by introducing. This is what Kostya was asking when I introduced Q. I did not do this numerics, but I kind of heard, let's say this way. That we introduce Q, you can like enhance strings, they become more exact, and when Q goes to infinity, well, Q equal to 1 is XXX, Q non equal to 1 is XXZ. When Q goes to infinity, it's called crystal limit, and then string becomes exact, and this bijection also becomes.
But then, do you know how these numbers on your Young diagram, how they translate into this KKR number?
Well, this is yes, of course. I mean, this is a precise algorithm. Yeah. So this bijection is an algorithm which allows to compute one from another, like systematically. Yes.
All right. So is it? Are you concluding now?
Yes. So this all I was able to say. I mean, so again, so one thing that I did not manage to fit in the time is that it's important part of the business to prove that all solutions to Bethe equations are actually eigenvalues of Wechsler Q operators. And well, but this is also true. And this is actually important part of proving completeness. Yes, and this is also done. Okay, then it's all. Thank you.
I have the question, or it's already the cutoff. Very short question. Do you know how to do it for other classical algebras like Dn?
No, but we are studying it a little bit now, yes.
I see. We also are sort of thinking about it.
Drama. Okay, any more questions?
I wanted to ask one question, but maybe I ask privately. It's more special.
Andrea?
Are there any more questions?
Excuse me, could I ask a question?
Yes.
So I'm wondering, basically this string hypothesis is more or less good approximation when this lambda goes to infinity, or the other way around.
When lambda goes to 1, it's the other way around.
Right. So it's like basically it's good when we are close to, let's say, no inhomogeneity or the same.
Yes, exactly. This is good when it's homogeneous spin chain.
Ah, okay. Thank you.
Well, but there is no really measurement how good it is, right? There is no parameter which says it becomes exact. It just looks good, but if you actually introduce some, zoom on some particular solutions, they don't look like strings at all.
Yeah, so it looks good, yes.
Yeah, but of course you can find, let's say, special solutions that look very different.
Well, I was speaking about with Jean-Sébastien Coy, so I understand what he's doing. He's like takes string solution as the first approximation and then plug it to Bethe equations and like improve it a little bit. So it's like a good seed point to start iteration to find the true solution.
Well, but we know this umbrella configuration is like very, very far away from it.
Yes. Well, but this is like far away from antiferromagnetic vacuum. So, I mean, for the guys, I mean, of course, he also observed like sometimes it fails and he cannot use ThinkUp as a first approximation. We know that umbrellas are far away. There is more funny stuff going on as well. I mean, Kolya has a paper about this, right? But so the statement that when it's good, it's like this some remarkably good like visually coincides. When not good, then it's not good. But when it's not good, that our prescription is still working, it's exact, but this is not.
Sorry, Dima. So eventually, what you talk now, this is the only regime you considered when your difference of data with alpha not exceeding beta, and the difference is not equal to h bar, or you have looked at the other regimes as well? When KKR is providing, when it could be related to KKR result.
So KKR string hypothesis for homogeneous spin chain when theta is equal to 0. Okay. Also when theta becomes different, the more different theta, the worse strings become.
Sure.
Yeah. So.
Yeah, I had a question. Since you were mentioning the umbrella solutions, how do you get them? What kind of Young tableau you'll have
right.
to start with?
You first fill the first row, then you fill the second row. That's all.
Mm-hmm.
This is like a typical umbrella, and it's better than like this row is longer than. So if it's the both rows are equal, then you get like very nice exact string, like in the middle. But the first row should be longer than the second row. And yes. the more longer the first row, the like umbrella-ish umbrella is. And but this is a solution when first you fill the first row with numbers and then you fill the second row with numbers. This is like the simplest umbrella. Yeah.
Okay, thank you.
All right.
So maybe, sorry, just a sort of more left field kind of question. So suppose I started, because I'd like to, take this back to say ADS. I suppose I started thinking, or maybe even about integrable field theories rather than spin chains. So I put some dressing factors in the game. Is there anything you could try to say about that?
Yes,
beyond.
Yes, I can. But yeah, so I'm not working on this now. So anybody interested, I think it will be interesting. So you see, so what is antiferromagnetic vacuum in this picture? What solutions for antiferromagnetic vacuum? It is well, it's like I say, it's kind of almost certainly true, but it's not proven, but the idea is like, first of all, we do SU2, that's only 2 rows of this Venn diagram. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So this filling is antiferromagnetic vacuum. Right, so if you want to make excitations, that means that somewhere you have to break down this pattern. And then it's interesting how to break it down. So a very interesting situation when you have to do PCM is to do like inhomogeneous spin chain with 2 inhomogeneities. Like one is very big positive, another very big negative. Like alternating spin chain, maybe you know. And then basically you kind of have this lambda to infinity, like you have 2 clusters of diagrams. One, like one part of diagram sticks to one inhomogeneity, another sticks to another inhomogeneity. And then there is something which is called jeu de Tocqueville, which basically these holes can propagate into the middle diagram. And so basically you have to describe the system by left adjacent diagram and the right adjacent diagram. And in the middle there will be holes. And these holes are actually like spinons. Yeah? So this is like a conjecture. And this is rough figure, and but I did not do some detailed studies of it.
All right, so should we then thank the speaker again? And then next week we will begin in a weird time, I think in the afternoon. Or is it at 3, Andrei, or at 1?
No, so presently we set it to 2, which would be 4 hours later than now. I don't know if it's particularly bad for someone. We can, I think, still move it around a bit.
Seems good.
So that's 2 London time, 3
2
Paris
London
time.
Okay. Yeah.
No, it will be a shorter telling a mystery talk.
Mystery, the title is a mystery?
Yeah. Maybe.
Surprise talk.
But I'm sure it will be interesting. So see you all next week. Thank you for coming. Bye-bye.
Thank you.
Thanks for the nice talk. See you next week.